Welcome back, class. Today we will be getting into the meat and bones of the subject of algebra. We started our course by discussing the nature of numbers. What is a number? Is a number a physical thing? Does it represent this abstract quantity that doesn't actually exist? We're just kind of like mapping our observations to these ideas, or are the ideas themselves some sort of a truth that exists beyond us as people, at which would imply that there's this metaphysical reality that we're in as physical beings? And then, well, of course, what does that mean? So then we discussed the topic of the properties, the specific properties of numbers, such as the fact that there's a family called the integers or the whole numbers, and they obey unique properties. And there's another set of numbers called the quotients or the fractions. They have their own set of properties. And then finally, there are these things called irrational numbers, and they again have their own unique properties. But regardless of the type of number that you might be looking at or analyzing, they're all going to obey the rules of algebra. And so we then introduced the different rules of algebra: the commutative law, the associative law, the distribution law, identity, inverse laws, et cetera, et cetera. And in addition to discussing PEMDAS, which is actually how you evaluate expressions that are written on a paper in a systematic way so that you're always obtaining the same quantity, we were able to show that whenever we write down quantities on paper, we should come up to the same answer, regardless of what specific strategy we use to analyze those numbers, as long as we are obeying the rules of algebra, and as long as we've all agreed on the convention, the social convention of PEMDAS, okay? Meaning that we all agree that we should, when we write parentheses on paper, we should evaluate those parentheses first. When we start to add exponents on the paper, we need to evaluate those exponents second, after we evaluate whatever quantities are in parentheses, so on and so forth. So we have agreed upon the way in which we will evaluate the various symbols that we've written on a paper. Okay, cool. So then this brings us to the topic of algebra, right? And before we get to algebra, we need to introduce a couple of terms, because sometimes the terminology can be a little bit unwieldy. Okay, there is a bit of a learning curve. You do have to learn these terms in order to be proficient in this class, because we're going to be throwing around terms all over the place. So let's start strong with the term variable. So what is a variable? A variable, simply put, is just a letter that we write down on paper that represents a quantity or phenomena. So often in physics, in math, in chemistry, we're going to be analyzing actual physical systems that are in the world around ourselves, whether this be, say, the data collected from a pharmaceutical company in order to determine whether or not a particular drug is effective or ineffective, or whether this be, the chemical reaction that might be taking place in a chemistry class, or say the orbit of the moon around the Earth. Regardless of the physical system that we might be analyzing, we're going to use certain letters to represent the properties of the physical system. So for example, T is a letter, and it might represent, say, the time that has elapsed of a physical system that we could be analyzing in the world around ourselves. Now, that being said, as we're analyzing these physical systems in the world, usually there is a numeric value that's attached to those observations. That's our observational data, right? So if we said that a car is traveling at 70 miles per hour, we might have a variable, let's just say speed, and we'd say that the variable speed of the car is 70 miles per hour, which is just represented by 3 letters. So MPH means miles per hour. It's a ratio or a rate that represents how fast a car is moving. All right. But nevertheless, just as a kind of shorthand convention, we will use these letters within the context of generally an equation or an expression. And there are all different kinds of variables that we can use. So like X, Y, and Z are very typical for this level of algebra. And generally, they represent the position of something. Okay, because oftentimes we're trying to model how things are moving in the world around ourselves. So that's like a really, really big problem is how do you observe something that might be moving? It's changing its state, right? From moment to moment, from second to second. And so, how do you analyze that? And then what do we do with that information? Another thing that's really important in the world around ourselves would be analyzing something like force. So the force on a physical object, such as like the weight of the roof on a building, right? You don't want the roof to collapse the building. So you need the weight of the roof to be a certain amount. You need like this, what is called the span of the beams that are holding up the weight of the building to be a certain distance from one another. If they're too far apart, then there will be some bad things that happen. So as it turns out. And then another quantity that's often represented in algebra would be something like mass, which is just represented by the letter M. Now, in our class, we're usually not going to be looking at, say, a specific problem statement, although in some instances, in particular chapter 2, and then I believe in chapter 4, they will give you some example problems that have physical quantities that are attached to the variables themselves. But usually we're just talking about algebra in general. And so we're going to use these letters to represent numbers, but then those numbers can change. So you should think of variable as variable, meaning the variable, the letter is able to change, from moment to moment based on, say, the observation. And just in general, a variable is a letter which represents a quantity or phenomenon. Now, this is different than what is called a constant. So any quantity which remains constant, as the name implies, i.e. it doesn't change, it is called a constant. A constant is a quantity which cannot change. So like the number 1 is a constant because 1 represents one of something out in the world around ourselves, or maybe it's this idea of 1, whatever that means. And so it's a thing. And if it wasn't 1, if it could change, then it wouldn't be 1 by definition. 1 is 1. If it could change, it would no longer be 1. So like say 1 changed to 1.1, then we would say it's 1 and 1/10. It's not 1 anymore. So 1 is a quantity that is constant. But in general, in our formulas, sometimes you'll get a formula like ax squared plus bx plus c. And these letters could be constants, and then those constants have specific properties. Usually the constants in a specific formula are chosen by the mathematician or by the physicist in order to make the equation work for whatever problem statement that they may be analyzing. Okay, this brings us to this term called an algebraic expression. So any combination of variables and or constants that is itself connected by either a sequence of multiplication operations, division operations, subtraction and addition operations, this is what is known as an algebraic expression. So for example, this nasty looking equation that I wrote here is an example of a algebraic expression. But then there are also, maybe less obtuse, less abstract examples of algebraic expressions. So like you could just have, say, x minus 5, that is an algebraic expression. 1/2 y, that's an algebraic expression. It's saying you have 1/2 of this variable y, whatever that means. And then you have b plus 2 over b minus 4. That is also an example of an algebraic expression. Now, often when you have an algebraic expression, you're going to want to evaluate the algebraic expression, which is to say, you're analyzing these physical systems, or maybe someone else has come along before you and has analyzed the physical systems. And maybe there's an equation that we've discovered, or maybe you've read in a textbook that there's an equation that models this physical system. And then the question is, based on the observational data that you have, can you use that observation along with this equation to model that system correctly? And so how do you do that? Well, you need to take the expression, i.e. the equation that you were given in your textbook, or the equation that you derived from your physical observations, and then you need to start plugging in the numbers. And that is what it means when you evaluate the expression. It just means to plug in the number into an expression. So you might have an expression like, say, b plus 3. So if you have an expression b plus 3. So this is our expression. And say we wanted to evaluate that expression at, say, b is equal to 4. Well, the notation for evaluating an expression so that you don't get lost in your math is to always put a vertical bar. Usually I'll put it to the right of whatever my mathematics happens to be. In some other places, they'll put it to the left, but it doesn't matter. However you want to do that. But I'm just saying we're going to evaluate this expression where we're going to take the number 4 and plug it in for where you see b. Okay, so b is equal to 4 just means I'm going to set my b value equal to 4. So when I do that, I recommend students use a set of parentheses to surround the variable that they're inserting into their expression. So you'll see I put a set of parentheses, and where my b used to be, I'll now put 4. Now, there will be students that say, Mr. B, that seems like a lot of work. It's so unnecessary. I already know what 4 plus 3 is. That's equal to 7. So, it's a lot of work to just write it down. But what I tell students is you're writing down numbers so that you're practicing the accounting step of the math process. So math is a process. It's not just like you've got this problem statement and then calculate the numbers. Okay, that's lower level math. That's elementary math. And that unfortunately trains students into this mindset where like all math is to them is performing these calculations. And they think, well, if I perform the calculation correctly, then doesn't that mean my math is correct? And if you were an accountant, right, and say I have a business and I paid this accounting firm $2,500 to do the accounting for my business, but say the accounting firm just comes back to me and says, hey, yeah, we did your accounting and we filed your taxes, and I asked them for a report on the specific deductions, et cetera, and they just tell me, no, we don't have that. Yeah, we can't do that. Or say I asked them to double check their books because what they're saying and what say someone else inside my firm is saying is in conflict. And so, and they say, well, we can't check our books because we never wrote anything down. It's just not acceptable. Okay. So especially if you're an accounting student, you really need to get in the habit of writing down your work, because in accounting, you can get in a lot of trouble if you make a mistake. If you make a mistake, whenever you're adding things up, that can literally mean the difference between whether you're in business or whether you not only get sued, but in some instances get put into prison. And the same is true if you're a student who wants to go into engineering. You need to be writing down every single step, okay? Every single step, and try to write things down in the way that I do it. I'm not just adding extra work. I'm practicing the best practices of the industry, and I'm showing you guys how to do it because my experience is in the industry. Like I have a company, I've built companies, I help some of my students build companies, and so I'm just bringing the practices of the industry to you guys, and so therefore, okay. All right, so secondly, students will often at this point in time express the sentiment that it seems rather unnecessarily complicated to introduce algebra before introducing a given problem. Like, I haven't even discussed what problems we're going to be analyzing, and here we are talking about algebraic expressions and algebraic equations, right? It seems like, at least in my mind, that algebra may be introduced backwards from the way that, say, we would talk about accounting or business or literally any other subject. It's certainly not the case that if you take a chemistry class, they'll introduce the math before they talk about how chemical properties work, okay? And so, and I would say, and then there are other students, myself included, when I was, taking this particular course, that without context, the underlying math seems like just a bunch of numbers and symbols, which is kind of analogous to children in church, like preschool or elementary school, trying to memorize entire Bible verses without having any theological context for what those specific verses are supposed to refer to. Okay, and the issue here is that the problems that we see in math are are super, super complicated. And the problems that you see in the world around you are super, super complicated and often require a team of people, not just one mathematician, but a team of mathematicians to actually solve. And so since the problems themselves are so complicated already, and what we're trying to do here in this class is we're just trying to describe the properties of the math and then analyze the actual properties themselves. And precision is required to do that, meaning, when I say 1 + 1, I need it to always be 1 + 1. I don't need there to be any confusion or abstraction or whatever. And so, unfortunately, words are up for interpretation. Whenever you write something down, there's a certain background of the reader that they're bringing to the table. And when they're reading your writing, they're interpreting the words that you say based on, in many instances, their cultural context. And not necessarily the context of the actual mathematician writing that problem statement down. And so 1 + 1 will always equal 2. But if I say the thing added with another thing, it's like, huh? The thing? What do you mean the thing added with another thing? And so at this point in time, let me stop sharing my screen for a second. And I will share my laptop screen. I just want to show you what math textbooks were like back in the day. So this is the Archimedes palimpsest, which is a scroll that was written on by various scribes. And this particular scroll dates to like 1000 AD or so. But it is a copy of a now lost work from Archimedes, who was a mathematician. And in this particular work, you'll see that back in the day, even though we can't really read Greek, and I'm not expecting you guys to read Greek, but you can kind of see that there are little Greek letters here. There weren't really numbers, okay? All of the math that was written down did not necessarily include the numbers to attach to the quantities themselves for whatever problem statement that was being talked about. And so what this meant was someone would have to spend years, literally years, 10 years, studying a scroll in order to understand the problem that was being talked about by a specific mathematician. And for these reasons, a lot of these scrolls during the early to late Middle Ages were lost. Okay, there are literally thousands of these scrolls that are just gone because people would read these scrolls, not understand what they were referring to or how to interpret what was written. And so eventually they were discarded because it costs a lot of money to make to make a book back in the medieval period. An average book would cost about $100,000 to make back in the day. And so, a book was worth its weight in gold. You would usually have one book per classroom in a college. Okay, you didn't have one book per student. You had one book for like 300 students, and you would have to come to the professor to ask a question, which was meaningful because the professor was the only one who had access to the text. And so you would really need to ask a lot of questions to your professor because you wouldn't necessarily even be able to read the text for yourself. Okay, so times have really progressed, but the point of this is to say that it was very, very complicated to work through mathematics without using algebra, without using symbols to represent numeric quantities and just trying to use words, because words are very imprecise, especially when we're talking about very, very abstract things such as what you see here. Okay, so switching back, say stop share. Okay. The last terminology or term that I need to introduce is what is called a coefficient. And a coefficient is just a leading numeric term and or constant that is in front of a variable of a given expression. So you might have an expression such as 3x squared the number that is in front of 3x squared, i.e. the 3, okay, this is the coefficient. The 3 is the coefficient of x squared. And we're going to see a lot of coefficients in this class, so it's really, really super important. All right. So transitioning a little bit before we look at specific examples of this section, let's go over square roots. So recall from the ending of Math 900, if you took Math 900, or recall from, say, 6th and or 7th grade, the idea of how to evaluate square roots. All right, so square roots are a little bit nasty looking. They usually have this little check mark symbol, which is called a radicand. And what the radicand means is it's asking the question. It's actually asking you a question. It's saying, what number multiplied with itself equals 36. So the radicand is just asking a question. It's saying what number multiplied with itself is equal to, in this instance, 36. And we would know that since, or because, 6 times 6 is equal to 36, we may conclude, and by the way, I use this symbol, which is like an equal sign and a little check mark next to it, to mean that we can conclude something from a fact. So I'm saying 6 times 6, we all know that's equal to 36. Therefore, we may conclude it is not the same as an equal sign, okay? We may conclude that the square root of 36 is itself equal to 6. Not only that, but you also have to be careful because technically speaking, whenever you take the square root, you're going to get both a positive and a negative number. Let's see why. Well, what's happening is that when you take a negative version of a number and you multiply it with itself, so say -6 times a -6, well, the negatives cancel out due to our negative laws, right? Negative and a negative is a positive, so you will have a positive 6 times 6. So that gives you a positive 36. So there are really two answers to this question of what number multiplied with itself equals 36. On the one hand, 6 times 6 self-evidently equals 36. But in a strict definition of that of the question, -6 times -6 also equals 36. Now, the confusing thing about square roots is that they obey a number of really kind of tricky rules. So just as an example, if you take the square root of a number which is raised to a power of 2, that's just equal to the original number itself. So the square root of a squared equals a. But then also somewhat confusingly, if you have a number that's underneath a square root symbol, and then you raise it to the power of 2, it's like the exponent cancels out the square root. So this is called the square root identity law, meaning that you can take the square root of a number squared and get the original number back, or you can raise a number that's underneath the radical symbol to the power of 2 and get the original term back. Another interesting property of square roots is that whenever you take the square root of two numbers multiplied together, it's as though you've taken the square root of one number multiplied with the square root of another term, whatever that second term happened to be. So just as an example of this, we all agree that hopefully that the square root of 36 was equal to 6, right? But there's also another reason why we can get to the conclusion that it must equal 6. Yes, obviously it satisfies the definition, but on the other hand, if we use this first and second property, we can also prove that we'll get 6 either way. So for example, we could have rewritten 36 as 6 times 6, which we already know. We know that 36 is 6 times 6, okay? But the reason we would like to rewrite it as 6 times 6 is that 6 times 6 is 6 squared. Remember, anytime you have a number multiplied with itself a number of times, we just say that number is raised to some power. So if you have 6 times 6, that's going to be the same thing as 6 squared. Now, if we do that according to the square root identity law, the square root will cancel the exponent and you'll be left with the original quantity. Cool? Now, of course, we know that quantity needs to be either positive or negative depending on the context. So we'll just write positive or negative 6. Now, another way that we could have gotten to that same result is if we said, all right, well, yes, 36 is the same thing as 6 times 6, but Mr. B, I seem to recall that 36 is also the same thing as 4 times 9. Okay, so the square root of 4 times 9, it turns out that what's going to happen here is that it seems to be the case that it's almost like the square root must be applying over the 4 and it must be applying over the 9, because when I take the square root of 4, that gives me 2. When I take the square root of 9, that gives me 3. 2 times 3 gives me 6. Interesting. Now, because of this second property, specifically the fact that you can take the square root of a number that's underneath the radicand, and if you've broken it up into a series of what are known as factors, right? This a times b, those would be factors of some bigger number that you can then apply the square root over each of the individual factors. Now, if you recall the fraction identity law, otherwise just known as the identity law, whenever you have a number, you can always write that number as a fraction. So like b over 1, right? So you could have said that this or I guess I should say not b over 1. Let me back up. You could have said that because any of these numbers that are being multiplied together can equal essentially anything as long as they are factors of some number, that you could have had, say, a term like b, and you could, instead of having b, you could say, let's let this represent 1 over some quantity, okay? So now you would have, say, square root of a times b, and it would be the square root of a times 1 over b, or simply the square root of a over b. And it turns out that in this case, because you've not done anything wrong, you've not really broken this number or this expression in any real way, you've just kind of redefined what b happens to be. And you said, okay, well, it can be 1 divided by some number, so long as these numbers multiply together to equal something. Then what's going to happen here is that this idea that the square root has to apply over each of the terms will still apply. So you would have the square root of a in this instance divided by whatever the square root of b happens to be. So let's look at that. So suppose you had the square root of 1 over 81. What's going to happen is the square root will apply over the top number, and then the square root will apply over the bottom number. Square root of 1 is 1. Square root of 81 gives you 9. So in this case, plus or minus 1 over 9 will be your answer. Now, how could we have reasoned that this square root law must work? Other than just say that, you know, Mr. B is the instructor, he must know everything, da 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 da. I mean, if you guys trust me, then you can just trust that this square root of a fraction rule works. But if you don't trust me, and by the way, I'll just write this. This is our square root fraction law of a fraction law. But if you don't trust me, you might need some further justification. And here's the way to justify it. So when you took the square root of 81, or 1 over 81 rather, you're still fundamentally asking the question of what multiplied by itself is equal to something. In this case, 1 over 81. And it turns out that what's going on is that if you remember the rules of fraction multiplication, how you multiply across the top and the bottom of a fraction when we're to multiply two fractions together. In this case, if you took 1 over 9 and you multiplied it with 1 over 9, well, you would have 1 times 1 in the numerator and 9 times 9 in your denominator. 9 times 9 is 81. 1 times 1 is 1. So what times itself is equal to 1 over 81? It must be 1 over 9. And you can do this with literally the square root of any fraction. So like the square root of 1 over 49. And you're asking yourself, well, what is this? Well, if you think about 1 over 7 times 1 over 7, multiply across the bottom, multiply across the top, you'd have 1 times 1 on top. You'd have 7 times 7 on the bottom. 7 times 7 is 49. 1 times 1 is 1. So your conclusion is 1 over 7 is the only number that fits the definition of a number multiplied by itself equaling 1 over 49. Now, of course, I don't expect any student to remember that's the thinking process in order to obtain an answer. There's no expectation in my mind that you should, or that this is even the best way to solve the problem. Instead, my recommendation to the student is whenever you see the square root of a term on top and a term on bottom, i.e. the square root of a fraction, just take the square root of the numerator and divide it by the square root of the denominator. Usually that's going to simplify things in such a way to where you're going to get a nice and pretty answer. Okay. Let's look at some of the problems for this particular section. In section 1.8, the chapter starts out with just giving you some expressions and having you evaluate the expressions. So if you look at problem, say 40 on page 69, so problem 40, page 69, you're going to see 3x plus 7, and it asks you to evaluate the problem statement at x is equal to 2. So it says evaluate the expression using the given number. All right. So what's going to happen here is if we drop the line below it, which is my recommendations to students, try not to do your math going sideways or horizontally. Try to do the math one line by one line by one line, because it's much easier for your eyes to catch a mistake if you're going from top to bottom than from left to right. Yeah, I don't know why that is, but it just seems like there's probably like a psychological reason for that. But it just seems in my experience that if I'm writing horizontally, I'm much more likely to make a mistake. And it's also been my observation that for students, they're much more likely to make a mistake. So we're going to rewrite the expression 3x plus 7, but where you see an x, please put a sequence of parentheses. I want to see a sequence of parentheses on everyone's paper. And then you're going to put your x value, which happens to be 2, into the parentheses. That's all we're going to do. We're not going to do the math in our heads. We're not going to jump ahead. We're just going to write it down because this is the accounting step. Now, once we're confident that we've written everything down, which, by the way, the textbook makes it seem like that's an easy step, but it's really not in the real world. It's really not very easy to know if you've actually plugged in the proper values where they're supposed to go in a real world scenario, in my experience. So, but nevertheless, in this case, we're confident that we plug everything in correctly. We've double checked our work. Everything looks good. We're ready for the next step. we're going to do, according to PEMDAS, the multiplication operation. First, do not add 2 with 7. You got to follow PEMDAS. You've got to follow PEMDAS. If you add the 2 and the 7 together, I'm going to be very upset. But we're going to do that multiplication operation because anytime you see a sequence of parentheses, you should know implicitly that 3 is being multiplied with 2 in this case. So we will get 6. And only now will we add the two quantities together. Now we've got 6 plus 7. That's going to give me what, 13? And that's my answer. Let's do a more challenging example. So this is problem 42. It gives us a kind of a nastier expression perhaps, and it says evaluate this for n is equal to 2. Here again, the first step of our process is to just write everything down, and where you see an n, we're going to plug in the number itself. So we have a n squared here. I'm going to put a sequence of parentheses and a 2 inside of the sequence of parentheses. We have a -4. Again, another sequence of parentheses. And put your 2 where that n used to be. +3. Now, scan through this. According to PEMDAS, we need to look at those exponents first. 2 quantity squared is going to be the same thing as 2 times 2, which gives you 4. And now we've got this expression. Go ahead and write one operation per line. It's good practice. You scan through this. We can't add the 4 with the -4 times 2. We can't add the 3 with the -4 times 2. So really have to attack that 4 times 2 operation. Note that there's a -4 times a +2 because the subtraction symbol is the same thing as adding a negative. Remember that a minus b is the same thing as a plus a negative b. Always remember that. So you've got this -4 being multiplied by 2. Negative and a positive is a negative. 4 times 2 gives you 8. So you've got 4 minus 8 plus 3. 4 minus 8 should be -4 plus 3. That's going to give us a -1. Okay. Let's look at using the distributive property to remove parentheses. So this would be problem 63. So they're giving you a expression and they say just apply the operations that are necessary to get rid of the parentheses. That's the question. So in this case, you need to go back and remember your distributive law, and specifically the left-hand distributive law. And it says anytime you've got a number just hanging out in front of the sum of two other terms, you can go ahead and multiply that number across the sequence of parentheses. So we're going to do just that. We're going to take the number that's hanging out in front. We're going to multiply it across the sequence of parentheses. We're going to have 3m plus 6, and that's what we're left with. Now, it doesn't matter for these problems where we're removing the sequence of parentheses, if you will. It really doesn't matter how many terms we have added or subtracted from each other. So problem 66 has something really, really nasty. It has like 6a to the 4th minus 4a squared plus 2, and it's being multiplied on the right by 3. And a lot of students are going to panic. Their heart's going to start racing. They see all these numbers. They're like, oh my God, Mr. B, I don't know what to do. The first thing you need to do is you need to take a deep breath. You got to relax. This is just math. It's not going to kill you, right? We're not running from a bear, guys. This is just math. So the idea here is we're going to rewrite our expression, and everything that's in the parentheses, you're going to write it in its own unique set of parentheses, and then the 3 will be written out in front because the 3 is the number out here. So let me go ahead and do that. You're going to have 6a to the 4th multiplied with 3, right? Minus 4a squared. That doesn't change, but it'll now be multiplied with 3. Plus 2, that doesn't change, but it's multiplied with 3. Again, take some deep breaths, guys. All right. So according to the associative law, so this is the distribution law, by the way. According to the associative law, you may remove the parentheses from the quantities that are all being multiplied by each other. So in this case over here, where you've got, say, the 6a to the 4th times 3, you can use the associative law to rewrite this as one single quantity, 6 times a to the 4th times 3. And you can also write this whole quantity here as -4 times a squared times 3. And you can write this quantity 2 times 3 as just, well, 2 times 3. Okay, however you want to do it, but that's basically what's happening. Also, you need to watch out for the negative signs, right? Like if this 3 was a -3, because you also have negative signs thrown into your expression, they're going to try to trip you up. They're going to try to make sure that you remember negative and negatives are positive. So the only reason why I've got my 3 on the inside there, as opposed to checking those negative signs, is that I'm dealing with a positive number to begin with. Okay, so now once we've used our associative law to kind of clean up our parentheses, we can now look at this first term on the left. You've got 6 times a to the 4th times 3. Why don't you get your numbers together with each other? So I'm going to do 6 times 3 times a to the 4th. And I'm going to do the same thing here. 4 times 3 times a squared and 2 times 3. Let's just go ahead and do that operation. That's 6, okay? 6 times 3 gives you 18. 4 times 3 is 12. And you're left with 6. All right. I need to see students understanding how to do each and every step on your paper. Okay, we had 4 steps here, right? We used the distribution, or rather 3 steps. I guess 4 if you include just simplifying. But the first step was distribution law. The second step is we use the associative law, right? The only reason we could move around these parentheses was because of the associative law. Then we went down, we used not the distribution law, but we used the commutative law rather, to move or shift your quantities forward or backwards within the parentheses. So like I could shift this 3 forwards or the 6 backwards, so on and so forth. And the only reason I could do that is because of the commutative law. And then finally, we simplified our expression, which gave us the answer. Okay, so let's do a combine like terms problem statement. So it says in problem, let's look at problem 76. It says basically to use combining like terms to simplify an expression. And the expression that it gives you is x plus 2y plus 5x plus 7y. So we're going to simplify this expression. Whenever you hear the word simplify, you need to be thinking in your mind, we're going from something nasty to something that's prettier, usually. So in this case, for problem 76 on page 70, we're going from something that's nastier to something that's prettier. We're simplifying the expression. So what does that mean for us to do, though, in practice? That means we are going to need to, in this case, use the commutative law to bring some of our terms forward and some of our terms backwards. Okay. So what did I do? We're given this nasty looking expression. I shifted the 5x and I parked it next to my other 5x, and I shifted my 2y backwards to park it next to my 7y. There's a reason I'm going to do this. There's a reason I'm going to do this, because the next thing we're going to do is we're going to combine like terms. So what is a like term? Okay. A like term is any expression where the sequence of variables and exponents are the same. Now it has to be both the variables and the exponents for you to have a like term. So in this case, the variable x and the variable x, this is the same sequence of variables, okay? So you would say that they're like terms. And what does that mean? That means if x was to represent an apple, you could say x just by itself. Well, that's the same thing as one apple. Okay, so this x by itself is really the same thing as writing one apple. And now I'm adding to one apple 5 apples, right? So in the student's mind, they should be like, okay, yeah, 1 apple plus 5 apples. All right, that's 6 apples in total. And similarly, suppose the y represents bananas. So you got 2 bananas plus 7 bananas. Because the y's are the same, those are an example of like terms. So you may write 2y plus 7y. That gives me, whoops, 9y. So our answer will be 6x plus 9y. That'll be our answer. Now note that like terms, identifying like terms can actually be a little bit tricky for a lot of students. You can have something that looks nasty like tx squared plus 7x squared. These are not like terms. These are not like terms because in one instance you have a tx squared, and another instance you have an x squared. So if you wanted that 7x squared to be a like term, there needed to be a t, another variable that's hanging out in front. But since that doesn't exist, you would say that they're two different separate physical quantities, and the tx squared is representing something totally different than the 7x squared. Okay, but you know, you could have something like negative 3x to the fifth and positive 2x to the fifth. Now, these would be like terms, okay? Technically speaking, yes, one is negative, the other is positive. But the only thing that really matters when you're identifying like terms is whether or not the variables themselves is the same sequence of variables, but then also whether those variables are raised to the same power or exponent. So in this case, you've got an x to the fifth and another x to the fifth. So you've got negative 3x to the fifth plus 2x to the fifth. You can say that this is going to be, well, negative 3 plus 2 is negative 1. So this will be negative 1x to the fifth. Okay. But a lot of students would ask me next, Mr. B, that's all great and dandy, and it makes reasonable sense. It sounds reasonable, but just because something sounds reasonable doesn't make it math, right? And I would totally agree. And so then the next question that the student would ask is there an algebraic way that we could have gone through the process of simplifying this expression? And I would tell them absolutely. So the idea of simplifying an expression or combining like terms comes from the fact that your distribution law can go in two different directions. So for example, if you have a say you've got b plus c in parentheses and you've got an and in front. We know that this is the right-handed distribution law, and it means that you're going to take the two numbers inside of parentheses, and then on the right, you're just going to multiply them by some value a, okay? But here's the deal. Take that x plus 5x. So we had x, or simply 1x, plus 5x. What's happening with combining like terms is it's like you're using the distribution law in reverse. So if we were to use the distribution law in reverse, we would take our term that's in common, which in this case happens to be x. We're going to park it out in front of our parentheses. And then the two terms that are not in common, i.e. the numbers or the coefficients, in this case 1 and 5, that would be the 1 and 5 inside of the parentheses. 1 plus 5 gives you 6. So we would be left with 6x. Voila. So that is how you can combine like terms just using the distribution law if that makes more sense to some of our students. All right, I will save the rest of the practice for our class period, and I will see you then.